So I want you to imagine, just for a second, picking up a bright yellow lemon.
Okay.
You cut it in half, and you just squeeze the juice directly into your mouth.
Oh man, my salivary glands actually just kicked into overdrive hearing you describe that.
Right. It's this involuntary, instant physical reaction. The sharp puckering of your face, your eyes squinting. I mean, almost anyone from any culture knows exactly what that feels like.
It's universal.
But if we pause in that moment, what is your tongue actually detecting? Because today, in this deep dive, our mission is to look at the fundamental chemistry of acids and bases.
Exactly.
We're going to see how that simple sour taste on your tongue is driven by the exact same invisible forces that, digest your food, balance your blood, and even reshape the world's oceans.
It really is all connected by the same underlying chemistry.
And the best part is, you don't need any prior science background for this. We are just going to take our time and really understand the why and how behind these everyday things.
I love that.
So to understand that sourness from the lemon, we first have to zoom way down, past the fruit, past the cells, down to a specific tiny particle, right?
Right. We are looking at the hydrogen ion because at the most fundamental level, what you are tasting when you bite into that lemon is just acidity.
Okay.
And acidity is entirely dictated by the behavior of this one microscopic entity.
So let's break down what a hydrogen ion actually is physically. I mean, a normal hydrogen atom is the simplest thing on the periodic table. It's just one proton sitting in the center and one electron orbiting around it.
Exactly. Now, if a chemical reaction strips away that single electron, the entire atomic structure changes. You are left with nothing but the bare proton.
So to the proton.
Just the proton. It has essentially zero volume. It carries a positive electrical charge. And because it's been stripped of its electron, it is desperately seeking to balance itself out.
It wants that electron back.
Very much so. It is incredibly reactive. And that bare proton, that is the hydrogen ion.
Okay, so acidity is simply a measure of how many of these free, highly reactive protons are just floating around in a liquid.
You've got it. An acid is basically any substance that, when you drop it into water, actively releases these hydrogen ions and pushes their concentration up.
So when you squeeze that lemon, the citric acid in the juice is just flooding the moisture on your tongue with bare protons.
Right. Or the acetic acid in vinegar, or the hydrochloric acid in your stomach.
Wow, okay.
And then sitting on the opposite side of the chemical coin is a base.
Right, bases.
Yeah, a base works in the exact reverse direction. So instead of adding hydrogen ions to the water, a base actively pulls them out of circulation.
Wait, how does it do that mechanically? Does it just trap them? Like a net?
Well, it can absorb them directly, sure. But very often, a base releases a counterpart particle called a hydroxide ion.
Okay, hydroxide.
Right. If a hydrogen ion is a bare proton looking for an electron, a hydroxide ion is basically an oxygen atom and a hydrogen atom glued together, carrying an extra negative charge.
Oh, I see where this is going.
Yeah, it is desperately hunting for a third proton. So when a hydroxide ion bumps into a free hydrogen ion, they immediately snap together to form H2O.
Ordinary water.
Exactly. The base has effectively scrubbed the free proton out of the environment.
That's wild. And I mean, we experience bases all the time, even though we don't always eat them. They have this kind of soapy, slippery, almost bitter profile, right?
Right, like baking soda or soaps or heavy-duty bleach.
Yeah. When you get a cleaning product on your fingers and it feels unnaturally slippery and you can't quite wash it off.
That slipperiness is not just the texture of the liquid itself.
It's not.
No, it is the base chemically reacting with the natural oils and fatty proteins on the surface of your skin. It's actively turning them into a rudimentary soap right there on your fingers.
Oh, wow. That's a little unsettling.
It is. That active chemical stripping is why strong bases can be just as corrosive and dangerous to handle as strong acids.
Okay, let's unpack this for a second because that brings up a detail that I think really confuses people. We use the words strong and weak in chemistry, right?
We do, yeah.
But people tend to assume strong just means dangerous and weak means safe.
Right, which isn't exactly the case. Strength, in this context, is a highly specific measurement of behavior. It describes how completely a substance gives up its hydrogen ions when dissolved in water.
I picture it kind of like handing out flyers on a street corner.
Okay, I like that.
Yeah, like if you have a strong acid, like the stomach acid we mentioned, it acts like a fully committed worker. You hand this molecule a stack of hydrogen ions, and it immediately, aggressively hands out 100% of them to the water.
Exactly. The reaction goes entirely to completion. Every single proton gets released into the environment the second it hits the water.
But a weak acid, like say the acetic acid in household vinegar, operates differently. You give that molecule the same stack of flyers, but it's hesitant. It only hands out a very small fraction of them.
Mm-hmm.
The vast majority of the molecules stay completely intact. They just keep their protons tucked away in this ongoing back and forth equilibrium.
But wait, think about this. If weak acids only release a tiny fraction of their ions, how is vinegar still able to, pickle and preserve food for years? Or dissolve rust off an old tool?
That doesn't sound weak at all.
No, it doesn't. And that is the paradox of a weak acid. It comes down to total capacity versus immediate release.
Okay.
While vinegar only releases maybe 1% of its hydrogen ions at any given moment, the remaining 99% are held in reserve.
Ah, I see.
So as that initial 1% gets used up, say, by reacting with the rust on your tool, the equilibrium shifts. The intact molecules notice the drop and release a little bit more to replace what was lost.
So it functions like a slow-release mechanism.
Precisely. This is why you can safely pour vinegar on a salad. It doesn't flood your tissue with protons all at once.
Whereas a strong acid of the exact same concentration would just dump them all and cause severe chemical burns.
Exactly.
Okay, so now that we know what acids and bases are, this tug-of-war of pushing protons into the water or pulling them out, we need a way to measure who's winning.
Right. Which brings us to the famous pH scale.
Yeah, you see it printed on everything. Skincare bottles, water filters, usually ranging from 0 to 14. But I think this scale is widely misunderstood.
It is, mostly because it is logarithmic, not linear. And that fundamentally changes how you have to read the numbers.
Because a linear scale is intuitive, right? Like a ruler or a thermometer, every step up is the exact same size.
Right. But the pH scale uses a mathematical trick to compress a massive, unmanageable range of hydrogen ion concentrations into those simple small numbers.
So each single whole number step on the pH scale represents a 10-fold change in the concentration of protons.
Exactly. Tenfold.
It's a lot like the scale used to measure earthquakes.
Oh, the Richter scale, yeah.
Right. If a magnitude 4 earthquake upgrades to a magnitude 5, the ground isn't just shaking a little bit more. The waves are 10 times larger.
Mm-hmm.
So if you have a liquid with pH of 5 and you drop it down to a pH of 4, you now have 10 times as many hydrogen ions. Drop it to a pH of 3.
You are at 100 times the concentration. If you drop it to a pH of 2, you are at 1,000 times.
That's crazy.
It is. Small, innocent-looking numbers are hiding massive, exponential chemical shifts.
So I really want people to internalize this. A shift of just 1 or 2 numbers is a huge deal. But that brings up a foundational question for me.
What's that?
Why is neutral a 7? I mean, why not 0? 0 just feels like the logical number for nothing is happening.
Well, the funny thing is, in chemistry, nothing is happening is rarely an accurate description of anything.
Fair point.
Even in perfectly pure distilled water, with absolutely no acids or bases dissolved in it, the liquid is not static.
It's moving.
Yes. The water molecules are constantly violently colliding with each other. And very rarely, but consistently, those collisions cause a water molecule to physically snap in half.
Wow, just from bumping into each other.
Yep. It splits into one hydrogen ion and one hydroxide ion. And then a fraction of a second later, they crash back together and reform into water.
So even pure water is constantly generating this tiny amount of acid and base.
Precisely. And because every split creates exactly one of each, the number of acidic protons and basic hydroxide ions is perfectly equal.
They cancel out.
Right, creating this very quiet, balanced background hum. Now, if you measure the actual concentration of hydrogen ions in pure water at room temperature, it's roughly 1 out of every 10 million molecules.
10 million. Yeah.
And mathematically, if you take the base 10 logarithm of that incredibly small fraction, you get the number 7.
Oh, so the 7 isn't an arbitrary center point at all.
Not at all. It is the literal mathematical translation of water quietly splitting and reforming in the background. Anything below 7 is acidic, and anything above 7 is basic.
That is so cool. And you don't even need a laboratory to map out these shifts. You can see this at home on your kitchen counter using an indicator.
Right, a substance that changes color based on pH.
Yeah, like in high school science class, you probably use litmus paper, which turns red for acid and blue for base. But you can just boil a red cabbage.
I've done this. It's a great experiment.
It is. The purple juice turns pink if you add an acid like lemon juice, and it turns blue or green for a base like baking soda.
And the reason that works is because the pigments that give red cabbage its deep purple color are molecules called anthocyanins. They are physically sensitive to the concentration of protons around them.
But how does the presence of protons actually change the color of the liquid mechanically?
It comes down to the actual physical shape of the molecule.
Oh, really?
Yeah. When you drop an acid into the purple cabbage water, those excess bare protons physically attach themselves to the anthocyanin molecules.
Hmm.
That attachment forces the entire molecule to twist and change its structural shape.
That is fascinating.
And once its physical shape changes, the way it absorbs and reflects ambient light changes. It stops reflecting purple light and begins reflecting a bright pink or red.
And so if you take a fresh glass of the purple cabbage water and add a base, the base strips protons away from the pigment molecule.
Exactly, which forces the molecule to twist into a completely different shape, one that reflects blue or green light.
Yeah,
You are visually tracking the invisible transfer of single protons.
that is amazing. Okay, so moving from the kitchen counter to the interior of the human body, biology actually weaponizes and carefully manages this exact pH scale, right?
Oh, absolutely. The biological management is incredibly precise.
Let's look at the stomach first, because it operates on an extreme end of this scale. Specialized cells in the stomach lining pump out hydrochloric acid, and they deliberately drag the environment down to a highly acidic pH, usually between 1.5 and 3.5.
It is an intensely harsh chemical environment.
Yep.
But it deliberately maintains that low pH for three structural purposes.
Okay, what are they?
First, it acts as a defensive moat, killing off the vast majority of bacteria and microorganisms that we inevitably swallow with our food.
Makes sense.
Second, it activates specific digestive enzymes that literally remain dormant until they are submerged in an acidic environment.
And third, it physically dismantles the food itself. Though I don't think melting is the right way to visualize it, is it?
No, not melting.
So how does the acid actually break down, say, a piece of meat?
It disrupts the physical architecture of the proteins. You see, the proteins in your food are long chains of amino acids folded into highly complex, specific 3D shapes.
Okay.
And those folds are held together by relatively weak electrical bonds. So when you flood that protein with highly charged reactive protons from the stomach acid, those protons interfere with the bonds.
They break them apart.
Right. The protein loses its structural integrity and unravels into a long, loose string. This is called denaturation. Once the protein is unspooled, those digestive enzymes can easily step in and snip the string into individual nutrients the body can absorb.
But here's where it gets really interesting for me. If my stomach is a vat of highly reactive, protein-destroying acid, why doesn't it digest me? My stomach is made of protein.
It's a great question. Biology has engineered a highly effective physical shield. The lining of your stomach continuously secretes a thick alkaline mucus.
Alkaline meaning basic.
Exactly. This mucus layer acts as a barrier that the hydrochloric acid cannot easily penetrate. It is essentially a constant, localized neutralization occurring right on the stomach wall.
So it's protecting itself in real time.
Yes. And when that mucus lining fails, or is disrupted by certain bacteria, the acid begins denaturing the proteins of your own stomach lining.
Which causes a painful ulcer.
Exactly.
Yikes. Okay, but in total contrast to the stomach, human blood sits in a very narrow, tightly regulated range, right?
Extremely tight. Human blood must be maintained right around a pH of 7.4.
So just slightly on the basic side of neutral.
Yes, and if the blood's pH shifts even slightly, the physiological consequences are immediate and life-threatening.
But why is that number so strict? I mean, we eat highly acidic foods, we exercise and produce lactic acid, our cells generate carbon dioxide waste. The proton levels must be fluctuating constantly.
They are, and the body fights relentlessly to correct them. Because remember how the stomach uses acid to unravel proteins?
Yeah.
Well, every single chemical reaction keeping you alive right now is facilitated by proteins called enzymes. And just like the cabbage pigment, these enzymes rely on their precise, folded 3D shape to function.
Oh. So if the pH of your blood drops even a few tenths of a point,
Excess protons will bind to your enzymes and subtly warp their shape.
it's kind of like bending a key just enough that it no longer fits into the lock.
Exactly. The enzymes misfold, they stop working, and cellular metabolism just halts.
Wow. So to prevent that bent key scenario, the body uses something called a buffer.
Right, chemical shock absorbers.
I find it really helpful to think of a buffer like a smart financial savings account linked to your checking account.
Okay, walk me through that.
So imagine your primary checking account is your bloodstream. For you to survive, that checking account balance must remain exactly the same at all times.
Which is a difficult thing to manage when random expenses and deposits are hitting throughout the day.
Right. So you link a smart savings account. In chemistry, a buffer system contains a paired set of molecules. one that can soak up excess hydrogen ions, and a partner that can release them if levels drop.
Right, usually a weak acid in its conjugate
Huh.
base.
So if aerobic expense hits like a sudden rush of dietary acid into the blood, the base component automatically soaks up those excess protons. It auto-transfers the deficit into savings.
And your checking account balance never fluctuates from the exact number you need.
Exactly. And if you get an unexpected deposit, the blood becomes too basic, the weak acid component transfers protons back in, it moves funds from savings to checking.
It's a brilliant system. Your lungs and kidneys are constantly venting carbon dioxide and filtering compounds to ensure those buffer accounts never run empty.
So that 7.4 number stays incredibly steady.
Yep.
But if buffers are how the human body survives pH changes, what happens when we scale up? Like when entire planetary ecosystems face massive injections of acidity.
Well, this is where that logarithmic math becomes critical on a global scale. We could look at the chemistry of rain, for example.
Normal rain is already slightly acidic, isn't it?
It is. As raindrops fall through the atmosphere, they naturally absorb carbon dioxide gas. The CO2 reacts with the water to form a very weak compound called carbonic acid.
But human pollution changes that equation.
Radically. The burning of fossil fuels pumps entirely different gases into the air, like sulfur dioxide and nitrogen oxides. And when those industrial pollutants dissolve into atmospheric water vapor, they don't form weak acids.
They form strong acids.
Yes, sulfuric and nitric acids. When this pollution-driven acid rain falls back to Earth, it causes systemic damage, particularly to soil chemistry.
Does it just physically burn the plants?
No, it's more insidious than that. It starves them. Healthy soil holds on to vital nutrients like calcium and magnesium.
Okay.
But when rain, heavily loaded with free protons, washes into the dirt, those tiny, highly charged protons aggressively swap places with the larger nutrient minerals. They knock the calcium and magnesium loose.
Oh, and then the water just washes them away.
Deep into the groundwater, entirely out of reach of the plant roots. The plants simply stop growing. And furthermore, it flushes toxic metals like aluminum out of the soil and into freshwater streams, which devastates aquatic life adapted to narrow pH ranges.
But there is actually a really optimistic angle here, which is great.
Yes, there is.
Over the past few decades, international policy efforts and targeted regulations on power plant emissions have measurably reduced those specific pollutants.
It's true. The acid rain problem in many regions has vastly improved.
Yeah.
It's a fantastic example of concerted policy efforts working.
Yeah.
But what's fascinating here is how this pivots to a current, larger concern, ocean acidification.
Because the oceans absorb massive amounts of human-released CO2.
Roughly a quarter of all the carbon dioxide humans release into the atmosphere. And as we mentioned with the rain, when CO2 dissolves into water, it forms carbonic acid.
Right.
Over time, the sheer volume of CO2 absorption is gradually nudging the ocean's overall pH downward.
And recalling the math we did earlier, because the pH scale is logarithmic, a modest drop in ocean pH means a massive, dangerous spike in hydrogen ions.
Huge. A drop of just 0.1 on the scale represents a roughly 30% increase in the actual concentration of hydrogen ions in the seawater.
30%. That is terrifying. And we always hear about the threat to the Great Barrier Reef, but what is the physical mechanism there? How does an invisible ion dismantle a reef?
It fundamentally disrupts how these organisms build their skeletons. Organisms like corals, oysters, and certain types of plankton build their shells out of a material called calcium carbonate.
Okay.
To build this, they pull dissolved calcium ions and dissolved carbonate ions out of the seawater and fuse them together.
But the ocean doesn't have an infinite supply of carbonate ions.
Exactly. And hydrogen ions are highly attracted to carbonate. When excess protons flood the ocean from the carbonic acid, they rush in and bind to the free carbonate ions, forming a molecule called bicarbonate.
Let me guess, they can't use bicarbonate.
They cannot. The excess protons are essentially hogging all the raw building materials. It requires the coral to expend vastly more energy to build even the smallest skeleton.
Wow.
And if the acidity becomes high enough, the solid shells of existing marine life can literally begin to dissolve back into the water to balance the chemistry.
Now, I do want to push for some clarity here based on the sources regarding the scientific consensus.
Sure.
The basic chemistry of CO2 making water acidic and binding up carbonate ions, that is undeniable, settled physics, right?
There is zero debate on the molecular interaction.
Right. But the ecological forecast, like how specific food webs will react or whether certain species of coral will adapt, that remains an area of active, genuine scientific uncertainty.
That is completely fair. Biology is remarkably resilient, But the sheer speed of this chemical shift is what scientists are actively studying. It makes adaptation incredibly difficult.
So after discussing the environmental toll, I feel like a listener might feel a bit helpless.
Oh, for sure.
But there is a built-in undo button in chemistry, a way to fix pH imbalances.
Yes, the practical chemistry of neutralization.
Mechanically, what actually happens during neutralization? We said earlier that an acid and a base cancel each other out, but matter can't just be destroyed.
Right, the dangerous components are just rearranged into harmless ones. When you mix an acid and a base in the right proportions, the hydrogen ions from the acid and the hydroxide generating character of the base immediately snap together to form water.
And what's left over?
The remaining parts combine to form a neutral byproduct that chemists call a salt. The overall pH gets pushed back toward neutral.
So you could theoretically treat an environment, like adding basic lime to acidified lakes or soil.
Exactly. Or taking an antacid, a mild base, to neutralize excess stomach acid.
Oh, that makes so much sense. And there's an even more relatable example that everyone listening does every single day.
What's that?
Brushing your teeth.
Oh, absolutely. The human mouth is an ongoing chemical battleground.
Yeah, because the plaque bacteria on your teeth eat the leftover sugar from your food and produce acid as a byproduct.
Specifically, lactic acid, which sits on the tooth and begins leaching minerals right out of your enamel.
But toothpaste is deliberately formulated to be mildly basic.
Right. To neutralize that localized acid before it causes damage, you're converting those dangerous protons into harmless water and salt right on your teeth.
It's just so cool. The next time you bite into a lemon, I want you to remember that tiny, energetic hydrogen ion.
It's everywhere.
It dictates the digestion in your stomach, the buffered stability of your blood, the chemistry of our rain, and the future of the Great Barrier Reef.
It really is. And as we wrap up, there's one final thought I'd love to leave you with, building on everything we just talked about.
Oh, I'd love to hear it.
We just learned how incredibly narrow the pH window is for enzymes in our blood, and how deeply life on Earth relies on the baseline neutrality of water, that pH of 7.
Right.
But imagine exploring an alien world where the oceans naturally sit at a highly acidic pH of 3.
Oh, wow.
How entirely different would the chemical building blocks of life have to be for an alien biology to consider an ocean of acid to be a perfectly neutral environment?
That is wild to think about. To them, our oceans would be a toxic, basic extreme.
Exactly. It just goes to show how specialized our earthbound biology really is.
Well, that is a perfect provocative thought to mull over. Thank you all so much for joining us on this deep dive. Keep questioning the everyday science around you, and we will catch you next time.